Alrighty, folks, I hope everybody's doing well. We are going to jump into module number 10. So I did a little bit of the rearrangement that I talked about and mentioned last time, just to make sure that we can get this latest assignment out so that you will be good to go. I might even push some other updates in here, but anyway, the assignment 6 will be due on the last day, so that gives you a little bit of flexibility, and historically it's not a very long assignment, okay? So by the time you watch this lecture, chances are the assignment 5 and assignment 6 will be in your repository, give or take a few hours here. Okay, so with that said, let's go ahead and jump into Module 10, where we're going to talk about scene graphs and terrain. This is a fun one. It's a pretty satisfying one. But just looking at the schedule here, you can see we're finishing up week 5, and, well, only 2 weeks to go here. It goes by quick. Just to give you, again, a little bit of an update, Lab 11 next Tuesday will be our last lab. I'm going to try to put out some content, not guaranteed, maybe some optional labs, even if they're just readmes or just something interesting about the topic. Sometimes I like to play around with this stuff too and keep iterating. So just keep in mind you might be getting some more labs after 11, but 11 will be the last graded lab, okay? And then the rest of the stuff, if I release anything, is just for fun. And I'll try to also have some materials related to these bonus lectures. Those will unlock too as the semester proceeds. So, you know, if you're missing this class by the time the term ends, you'll have those bonus lectures available that you can always take a peek at. All right, now we'll actually jump into module number 10. So as always, don't forget your in-class activity. And I have the slides here ready to go. And we're going to talk about 2 topics today, but we'll get into it first here with a little fun pre-class warm-up, or at least something that I think is pretty neat. And the reason I think it's neat is because, one, I'm always fascinated with rendering water. That's what's being shown on the picture here. But I also like techniques that are really simple but clever. So there's a blog post here talking about how they render water in the video game Super Mario Sunshine. Now, this is a relatively old game here. So it's, in a sense, they had to make these sort of graphics hacks and try to make stuff work that was easy. Let me see if I can refresh here or open it in a different browser here to see if it'll run. So if you can't see the effect, Firefox is usually pretty good. But here it is, and it looks really nice here, this water effect here. Now let's see if I move around the effect, maybe you won't see it here. Let's try to make it full screen here. Oops, well, it went away. Let me just refresh it. But all it's really doing is using 2 textures, okay? It's kind of a neat effect, and we know how to texture things, so now we just have to go as far as using 2 of them. So anyway, let me see if I can scroll up without breaking this thing. So here's the nice water effect. Sorry, it was just scrolling for me. The finished product, and you can see sort of towards the beginning here, there's no waves, I guess, because, you know, if you go to the oceans, when you look out, you sort of see over the sunrise is sort of speckling and so on here. But all it is right here is a textured plane. You can't see it, it blends in with the website here, but just a plane here. So we've figured out how to do that previously, render 2 quads. Here it is again, and here it is this time where they've placed 2 textures on, but if you look, all the texture is doing is actually scrolling back and forth. You have one going this direction and one going, I think it's going a little bit vertically, and there are 2 textures just scrolling on top of each other with a little bit different textures and a little bit of translucency. Here, I'll move it around a little bit. But you can see that's all it is, and it's a repeating pattern here, okay? But with a little bit of magic, or I won't say magic, but a little bit of math here, and the idea of mip mapping, which we talked about, but sort of generating mip maps in the way that the closest thing to you is just blank, and then you have your different levels of mip map. That's how you get these sort of waves that look much more detailed when they're further out. Remember how we talked about mip maps and this ability to choose a texture based off of how close you are to the that particular texture or object, and then objects that are further away are rendered with a different, often less resolution texture. Okay, so here's that effect being applied here. And then finally here they add a little bit of a blending function here, and you get the final water effect here. So from wherever your camera is, wherever you're viewing those fragments, I might have broken it, so you can you can play around with it a little bit. It gives you a really nice effect here. So I'll just go back to the top and show it off one more time. I think this is really cool. And this would be something fun, for folks who want to do a rendering project on their final project. So speaking of which, let me jump back into the course website. Just final project deadlines. Hopefully folks are finding their project. I've consulted with a lot of people during office hours, and that's been hopefully very useful for them. But for other folks who don't have an idea, posting on Piazza, asking myself, course assistants, etc. On particular projects would be good. Otherwise, looking at some of these other project ideas are good, and anything sort of fair game, if it's been created before or you want to alter it in some way. Okay, and you are welcome to build off of some of the previous assignments. You just need to make clear what the contribution is that you're adding onto that project. Okay, all right, so back to the slides, past the warm-up here. Last lecture we were talking about normal mapping. That was how we sort of ended things to get you ready for your next assignment, which I'll push out very shortly as well. We talked about, what is this tangent space matrix? Well, it's basically a way to get our texture coordinates or our normals that we've pushed onto a texture. Okay, that was that bluish sort of image. That's called our normal map. But it's a way to sort of get them to respond to, well, whatever our transformation is, however we're viewing or whatever direction we're viewing this particular object and what its orientation might be. Because remember, when the normals are generated, they're generated in one specific position. So we have to be able to rotate those normals in a sense, and we do that by multiplying them through this matrix here. Okay. And then we talked about, and what you implement in your lab was this idea of multiple lights. And primarily, a big goal of this lab was, one, to learn about point lights and the importance of lights, but also just to see the functionality and the power of GLSL. It really is a powerful language, and it's got functions, it's got loops, it's got all those different things. So those were some primary takeaways from last lecture. All right, so again, assignment 5 will be out. Assignment 6 also shortly. I'll be pushing those. I'm updating the abstraction a little bit for the starter code, so that's just taken me a little bit longer. And you'll see the updated abstraction with today's code. I just want to make sure that they match. So I will push those out, and you will have those at some point this Friday, and then be able to get started. Okay, and assignment 6 really is a relatively short one, so I'd recommend knocking it out as soon as possible, and then you can just focus on the final project. All right, so today's topic, though, is about scene graphs and trees. Okay, so many labs ago, if you can recall, or maybe not that many since it's such a short semester, we were able to render two different objects. Okay, and we had a abstraction for this, right? We had this object class, so we could create my object or my object2 or whatever in our STL graphics program, and then render these objects. Okay, but again, if I asked you to render 100 triangles, how would we do this? Well, you could sort of do it this way. We could just create a bunch of objects. Of course, you know better as you're learning C++. You could create a data structure like a vector, maybe a loop, and maybe manage these objects in some way. In fact, we built a little object manager class last time, or at least you got to see an instance of it in the last lab. That this is something that exists and maybe could be useful for solving this problem. But the reality is, when we're creating graphic scenes, we have just a lot of objects, okay? Sometimes hundreds, sometimes millions, depending on what type of game you're playing, or if you're doing something maybe not necessarily a game, but a movie, you could have millions of objects and as much detail as you want, okay? And usually, if you're building this in a tool, whether it's a 3D tool, a game engine, a tool that you're building, usually you'll have some sort of scene hierarchy here, and it'll tell you, where your objects are. And you'll have other things too in your scenes, like lights, perhaps cameras, lists of the geometry and so on, but you'll have all these things contained somewhere here. And here's just another view of looking at a scene here. Here's a simpler scene here, but you'll see this tree view. And it's the same thing that you see when you open a file browser, when you have directories and files that sort of fall under it. But it's this tree view, you can tell or at least see that it's organizing your scene's 3D data or other entities, whether those are cameras or lights or collision boxes or whatever that might be. It's all organized here in this tree structure. So you can see you have a root here, which is sort of your world, and then you can group things or just have these sort of nodes freely standing for your camera, different meshes, or your geometry here, okay? So this tree data structure is what's known as a scene graph or a scene tree. Sometimes it goes by scene graph. It usually is a tree though, you don't want cycles, but you'll hear it called scene graph. And I like scene tree a little bit better. Okay, so scene graphs or scene trees is a hierarchical tree data structure that's used to organize graphic scenes. Okay, and there's several ways to organize them. Here's the one that I showed here, and you kind of figure out what your nodes are. Are they going to be cameras? Are they going to be lights? Everything just going to be some sort of entity, and then you'll define the properties later. Those are some options that you have. Okay. Now, basic scene graph is relatively flat, meaning the height of the tree is relatively low, meaning I'm not usually traversing down too many levels here. But it may be possible. There's no restriction. And again, you can hold things that are not necessarily geometry. Okay, so this particular instance is showing the geometry here, but you might also have textures as nodes here, and maybe those will apply to things in some way. But one of the real powers, or why I'm talking about this, and why I'm moving a little bit away from our little object manager idea where we just add a bunch of objects into our scene, is because scene graphs, we can store anything. We can actually store transformations on objects, okay? And something that's really hard to convey in a single object is a relationship between another object. Okay, so let me just sort of describe it with this picture here if I draw your attention to the right, if you're wondering what this thing is. But basically we have a pivot point here. This blue thing's an object, and then we have an arm here, that's the red, and then the green, another arm. And the blue pivot point is rotating. And I also have this red object under the hierarchy, or it would be in my tree, a child of this blue object here. And what's happening is this red arm is inheriting the transformation or the rotation of the blue thing. Okay, and then likewise, the green is also inheriting the rotation from the red, and maybe it's rotating a little bit too after. Now this is really hard to, especially as the hierarchy gets deeper, to programmatically do. Right? We've learned about how matrix transformations compose and so on, but if we can wrap these in a nice way so every object has their own transform, and then we can describe the relationship with them, meaning parent or child, then it becomes easy to model some of these things like a pendulum swinging here, okay? And you can have different constraints here, okay? So that's the idea. You can propagate through a hierarchy the transformations or whatever other properties you might want to do. Okay, so here's another example of it. This is the robotic arm, which is sort of a classic problem. If you ever take a graphics animation course where you can see that the cylinder can rotate, and then these arms here can, these are hinge joints that can bend up or down, and that's sort of the constraint. And then you have to figure out how to program this thing to put the blue disk in these different positions, okay? So again, though, that's one of the powers is you can have these constraints on your different objects or model them in some way, and then when they work together, you're simulating a machine here, or something more complex like human anatomy, right? Our shoulders rotate, our elbows bend one direction, and you can sort of model how that works in a much more complex animation. So you can see this character here has lots of different joints and bones and stuff modeled in this hierarchy if you look really close. And then when they fall, you're able to sort of do this physics simulation here to say, okay, if the arm hits first, then The torso is sort of going to follow with this momentum, but it can't bend, all the way back because it's constrained. So anyway, this is a really nice way to model this character and get realistic behavior. Okay. And you can sort of do this example yourself, right? If you go ahead and take a moment, and I'll bring myself on the screen here just for the moment. I know I'm a little bit blurry, but if you go ahead and do this experiment where you just try to walk somewhere, right? When you walk somewhere, your torso is going to come along with you, your shoulders, your hand, etc. Everything's going to move with you. When you step your leg forward, the rest of your body should follow with you. So that's the idea. That's what we're modeling. We have our own sort of hierarchy. If you want to think of your head as the root and then your torso, your arms, legs, etc. That's, again, what's being modeled here. And you can just use yourself as an example, which is kind of fun. So anyway, let's go ahead and proceed forward and just see some useful examples. And scene graphs, they're not limited to just what we're going to model, like that sort of human interaction. Now that's going to be an important thing for us to also organize our scene, but they can also be used for optimization. So if our scene is sort of modeled as this tree, and for example, if you only see objects in a particular group, you don't have to render the objects that are behind you, okay? So that's what this little animation's showing here, right? Here's your view box that you can see. So anything that's not in the view is being clipped away, but that's just another use of your scene graph, right? If this biggest node isn't within the view, well, if it had other objects within it or other lights or other, cameras or whatever other entities there might be, you don't have to worry or waste processing power on it. So scene graphs and scene trees are very useful also for optimization. You just don't have to render the children. Okay, so how do we enable the scene graph data structure? Well, the first thing we need is a transform data structure. Okay, and we actually already had this in your previous lab. You might have noticed it, some new things popping up here, but here's the transform class. I want to briefly talk about it just so you have an idea. It contains now a 4x4 matrix, right? And this is your sort of model transform. So whatever this transform is you're creating, it has its own local transform here. It's going to have other operations for manipulating whatever the entity is here. I'm calling it an object, but it could be any entity. So you can translate, rotate, scale it, whether it's a light, a 3D object, a camera, whatever it is, and whatever it means to translate that, rotate it, or scale that particular entity. You'll have a function for loading the identity, which just resets an object to the identity matrix. So essentially clearing all these transformations, right? That's the matrix with the ones all across from it. Okay, and we'll have abilities in our graphics framework for retrieving the matrix. So we can retrieve any of these transformations that we've done, as well as essentially compose these particular transforms. So there's also going to be a useful function here for applying a transform. So if I have one object and I'm able to get its transform, well, I can apply another transformation to it, okay, and set that transform in some particular way. Okay, so I can get a transform from some other object if I wanted to move with it and essentially transform it. Okay. Okay, so this is going to be our structure here. And again, really all it's doing is it's wrapping around a GLM 4x4 matrix. We could just use these 4x4 matrices and achieve the same idea, but it's nice to have everything wrapped in a transform class. Okay. And that'll make it a little bit easier to compose things if we can just retrieve that matrix and then perhaps apply it to other transforms from other entities. Okay, so how are we going to structure this scene graph or scene tree? Again, if you're not as familiar with this, well, remember a scene graph is a tree. Again, it's usually named terribly, but scene tree is really what it is, and I keep calling it scene graph. Tree is a special instance of a graph without cycles, both technically correct. So anyway, a tree is a hierarchical data structure. So you have a root at the top. This is your parent. This is where your scene's going to start. If you want to think about this as the giant landmass or Earth or something where we all sort of revolve around, that's fine. That's a nice way actually to think about it. And then you have child nodes from the roots above it. So this is the parent node 4 of node 2, and that's the basic things that you need to know about a tree. Something at the bottom of the tree is what's known as a leaf, and it has no descendants, right? These children have no other children of their own. So again, with a scene tree in graphics, typically, I'm trying to think maybe there could be some situation where you'd want to cycle. But anyway, trees don't have cycles, so I don't have any nodes pointing back up on the tree. It only sort of goes down one direction. It doesn't go across to any of the sibling nodes or anything. But the objects that we have and their transformations are going to propagate downwards. It doesn't have to have only 2 children either. It can have any number. That just happens to be what's in this picture, but we looked at some examples. In fact, let me just go way back where we can have multiple children here, and that's okay. Okay. Okay, so how do we implement a tree? How's this data structure going to be implemented? Well, here's a very basic tree. If you're going to do this in C++, you'd have this sort of tree structure, some way to traverse the tree. You want to know what your root is, and maybe you can set that, maybe you can change it, but by default you'll have some root for this tree where you want to start from. Okay, that's the very first node in your tree. Again, that could be the planet Earth, if you will, if that makes sense to think about it that way, where everything's going to revolve around. And then you'll have tree nodes, which is what your tree consists of. So here's your tree data structure. It consists of a tree node. And these are the actual nodes in the tree. And then those can have any amount of child nodes themselves. So you can use some data structure like a vector, for instance, to have pointers to these other nodes. Okay, that's effectively how you get that branching effect. Add one node as your root, and then it can have any number of child nodes that you push onto it. Okay, and then the process can continue. Okay, so anyway, to implement a scene graph or a scene tree, we have to figure out what the relationships are that we want to have. Again, each object can have those additional child nodes. That's what is shown here in this vector here. Okay, and we sort of want to be able to mimic, this structure here. Okay. That's exactly what we're going to be working on in the next homework. So let me advance us just a little bit here to give a little preview. There are some supplements for this, but what we're going to be building is a little solar system, which is a nice example of a use of a scene graph, right? Where we have the sun, and then the Earth revolves around the sun, and then the moon revolves around the Earth. Okay, so that's a sort of transform here. Wherever your sun is, you're translating out where your Earth is, and then your Earth is going to also rotate. So you'll do a translation and then a rotate. So you're rotating around this way. But as you're rotating, you also want the moon to rotate around the Earth. So the moon is going to locate, in a sense, where in the solar system is the Earth. You're applying the transform from the Earth to the moon, and then the moon can also rotate around the Earth. So as the Earth rotates, the moon follows wherever the position of the Earth is and rotates around it. So in a sense, the origin of the world, or the moon's origin, is sort of the Earth's origin is the sun, and then that's how you get this sort of interesting rotation. Okay. So what you'll be given, it is in today's support code as well, is this scene node class. This is all you really need here. But you'll have a sort of root scene node, and then it'll have the ability to find its parent. So you can look up the scene tree and grab the transformation from your node above you, and then you can, from once you have your parent's transformation, apply that to yourself, and then apply any other of your sort of local transformations that you want. Okay, so there'll be a little bit of a README for assignment 6, but I promise I think it's, if I remember correctly, only a few lines of code of changes that you need to implement. Okay. To actually get it working, which is pretty neat. You could certainly improve on this abstraction if you like, but it's relatively short, and it's a fun and satisfying result. Okay, and here's just an example of the solar system here. We've had a few final projects that build on this type of thing here. But anyway, you can see that here's the sun, here's some planets revolving around it, and some moons around these planets. That's the idea of what you're building. All right, so we'll shift gears in a moment. So if you need a break, go ahead and take a break, and then we will continue. Alrighty, so with that said, let's go ahead and continue onwards with our discussion of our next topic, which is going to be to talk about terrains. All right, so terrains are a fun topic, and rendering terrains is really it's a well-studied problem in computer graphics, but it's something that always needs more studying. Whether you're thinking about it in terms of what people do for simulation, sort of GIS data, this is what a surveying a satellite or an aircraft might survey the Earth and populate for Google Earth, or for gaming applications, landscaping, etc. This is really a area that you could spend a lifetime studying how to render and simulate the Earth, again, whether for movies, graphics, games, or simulation purposes. Okay, so anyway, let's continue onwards. And the question is, how do they render these fantastic environments? So this is a screenshot from the game Horizon Zero Dawn. Again, doesn't matter if you care about games, but this one, even a few years old, just looks pretty magnificent if you're looking out into the Earth here, and you can see the clouds and the foliage with the trees and stuff add some more realism, but pretty impressive detail here, especially as you look at the rocks in the sort of foreground here. On just how things are modeled there. So again, remember, as breathtaking as these scenes look, everything is just a triangle. Okay, so that we've focused on that in this course. There are actually other techniques for doing things not as triangles. Folks who have played Minecraft, maybe you'll understand this term voxel, which is sort of a blocky world. And for those who haven't seen Minecraft, let's just bring up a screenshot to keep everybody in the loop here. But it sort of models this world, but you just have blocks here. So it almost looks like Lego blocks. That's part of the style. So that's one way to model a world. But we've talked about everything in triangles in this course here. Okay, all the way back to our homework 3, which most folks here have wrapped up very recently. Just for how to take some geometry in and rendering it, right? And we could sort of model these. We could certainly use an art program like a Blender or a Maya to model a world here. That would certainly be acceptable. But so here's an example in Blender of a tool that sort of automatically generates a terrain. It's essentially moving around some vertices in interesting ways, right, algorithmically. Then you could export out this model and load it if you wanted here. But I want to simplify the problem a little bit and show you a cool technique. Again, utilizing texture data to do this. Okay, so if you've ever seen these folks around campus or in a city you live in, or near some construction zone, they're essentially surveying the land. Okay, they're probably doing many other things. Civil engineers are always doing interesting stuff, but essentially, if they're surveying the land, seeing how it changed, and one of the tasks is to actually measure the elevation here, these peaks and valleys here. Okay, make sure that things aren't slanting or whatever, for whatever dangers that could provide, right, in a city or elsewhere. But anyway, what you see here though is this flat grid of this terrain, and it's sort of broken up into segments here. Okay, representing the world here. So I wonder if we can sort of represent this flat grid in OpenGL, and then based off of the elevation, just sort of pop up some vertices, and that would be a way to represent a terrain, right? So if we can sort of draw this grid in OpenGL in some manner, that's what we need to do. Okay, so we can't draw it like this. We need triangles, so we've got to draw it like this. So how do we generate one of these triangular grids here is the question. Okay, so let's go ahead and take a look at a new primitive. So it's still a triangle, but it's something called a triangle strip. Okay, so it's a series of connected triangles which share many of the same vertices. So you can see, for instance, if I pick on this one here, vertex 4, it's shared along this edge here, V2, V4 to V3, V4 to V5, and V4 to V6. Okay, so it's sharing many different other triangles here. It's got a lot of neighbors in a sense here. Okay. And this is good because it makes the the terrain that we're going to render much more efficient if we're able to not have to create lots of individual vertices, right? This is where our index buffer comes in. So we just have one index here, vertex 4, and it's shared amongst several other triangles in order to create several other triangles. Okay, so that's the idea. So how do we do this? There's a little bit of a challenge with drawing the triangle script because, well, first we just want to sort of plot our vertices here. Okay, one after the other. And we can sort of have a loop within a loop to do this, or even just one loop for however many vertices we have, and plot them on the x and the z axis. Okay, so I'm looking on top of this image, just to be clear here. Okay, so at this point, if we do that, now how do we optimally connect each of these points to form the triangle strip? That's the question. Okay, so if we first just start adding an indice here, first 1 to 6, then 1 to 2, that's our first triangle. Okay, and then to make our second triangle to draw a quad, well, I can reuse some of these indices. So I have 2 to 6, okay, then to 7, and then back to 2, okay? And that's how I create my next triangle. Okay, now you saw this pattern where I kind of went 1, 6, 2, 2, 6, 7. So I'm going down a row, whatever my length is here, or a pitch, sometimes we call it, the pitch or the width of this terrain is 5. So I go 1, then I have to add 5 here, and then I go back to, well, wherever I started and add 1, okay, to whatever this index is. So these are the indexes of these vertices here that have been plotted out, okay? So now challenge yourself, see if you can figure out what's the next triangle going to be. What's the next pattern? Okay, so the pattern is, I'll give you a moment to pause the video. If you've paused the video and are joining back here and have figured out the pattern, maybe by drawing some of these points on a piece of paper and trying to connect them to get this sort of same pattern, you go 2 to 7 to 3, 3 to 7 to 8, 3 to 8 to 4, 4 to 8 to 9, 4 to 9 to 5, 5 to 9 to 10. And then when you reach the end here, 10 to 5, well, you need to realize that, okay, we need to, when we're drawing our next triangle here, we have to jump down to the next row and start indexing there, okay? So this is the pattern here, that same sort of pattern here that we were doing here. We go 2 to 7 to 3, 3 to 7 to 8, okay, 3 to 8 to 4, 4 to 8 to 9. So every time we're drawing, one quad at a time, then eventually we skip down here, and then we reuse some of these indices. Okay, so that's the pattern. Okay, so what you're going to be doing today, what the challenge is for your lab, and these slides will serve as good guidance if you get stuck, is you're going to be implementing in 3 pieces. Okay, in the terrain.cpp, how to create this grid. Okay. The grid and a little bit more of that. Okay, so you'll have the constructor here where you're constructing the grid. Okay, and here's what it's going to look like, right? I'm not trying to be tricky here, but one part of this is going to be generating the grid of vertices, right? So how do you do that? How do you just generate random points? And then the second part, that's this lower part here, is how do you connect them together? Okay, so how do you select the right index? So the challenge before you try this lab, so this is your support code if you need it, to complete this, is to try to figure out how would you loop through and grab the right indices, given that you know what the length is of this triangle strip here, right? It's 5 vertices wide, okay? And in this particular one's 2, in its height here in the z dimension. So if you can figure out this pattern here, that's a great exercise. And of course, you have it here as support code if you need it here. Okay, now there is something new here though that's kind of interesting. I'm not just adding the vertex x, y, and z, but I've also got to add some texture coordinates u and v here. Okay, now why do I want to do this? Well, what I really want to do is, our terrain, if I go back here a little bit, is pretty boring if it's just triangles, right? And we've learned about textures as a way to add detail. So I want to actually map a texture on top of this, okay? So I've got to figure out, if I have one image, how do I map the texture coordinates to each of these vertices? Okay, so that's your next challenge. And again, you've got some support code for helping you do this. But this is the idea. This is the support code to figure out, which segment am I on? So is it this little tiny square here? this first part of my texture map here, or the first part of my grid here. Is it here? Am I here? Maybe I'm in the middle somewhere. Wherever I am as I'm sort of marching through and plotting those vertices, I'm also computing the texture coordinates. So some range of 0 to 1, maybe it's 0.5 if you're sort of towards the middle here, and 0.5 for that particular vertex. And then you're essentially taking this image and then dropping it down onto the grid. Okay, so you're dividing it up into little pieces. Maybe it's little increments of 0.1 or whatever your width is here. So that's what this is doing, computing the U and V or the S and T coordinates of the texture. Okay, that's your second challenge. Okay, and part of that's taken care of here. Okay, okay. Now the other thing that we want to do though is not just generate a flat grid, but we want to make it interesting. We want to add height here. Okay, so this is enough to get the texture coordinates and then to sort of plot it out, a textured grid with a texture on it. Okay, but we want to add height. Remember what those surveyors were doing in our example? They were observing the height and marking it down. So where can we get this height information from to create something sort of interesting? And the answer is, well, in our constructor, we're actually going to have some height data loaded up, and we're going to grab that from a texture. And this is a really neat trick here. Okay, so here's where this is being applied here. But our texture is also going to have a second texture. So we're going to have one for the world and one that's just a grayscale color image. Okay, and each pixel here represents the height. Okay, whatever the color is. So if it's black, that's a RGB value of 0. If it's white, that's an RGB value of 255. So that's going to set our height to, or our Y value to 255 if it's a white pixel. If it's 128, something grayish, then it'll be 128 units high, etc. Okay. And because this is a grayscale image, we really just need to read one of these color channels here. We have it in RGB form, but we can just read the R, the G, or the B pixel, doesn't matter, to get our height here. Okay, so the lighter the color, the higher the Y value, and the lower the value, the lower the Y value. Okay, it's just scaling from 0 to 255. And of course, in OpenGL, we usually read these in as floating point values and just use 0.0 to 255 will be our range. Now we can also scale this, so I am going to have a scale factor. You'll see that in the lab, because otherwise the train will look a little bit too choppy. The difference between 0 to 255 is very stark, so I actually do divide this by like 5 or something, just to make it a little bit nicer. I'll show you the example in a moment. Okay. Okay, so anyway, what we're doing is we're creating a grid. It happens to be 512 by 512. That's how many pixels our image has. And that's how many pixels our corresponding height map here have, the black and white image, or excuse me, the grayscale image. Okay, so here's an example of what you'll see. This height map corresponds to, if I texture and use this data on our train, it generates this image here. You'll see the more lighter colored values here are higher. They're the peaks here on our mountain versus the lower colors. So maybe this is an ocean or something down here. Okay, so that's our challenge number 3. Okay, now this is if you lay the texture on top of your on your world here, right? So you're sort of texturing the world with your height map, and this looks pretty cool, and it's a great way to debug what's going on. But oftentimes we want color, right? We want an actual world here. So we're actually going to overlay. We'll have a diffuse texture map, and this is what we're going to sample from in our shader here, this particular color map, okay? And somebody hand painted this, and I believe they procedurally generated the colors. So they said, hey, if any value is less than 25, take this image and color it blue. If it's between 26 and 50, make it sort of dark green. If it's between 51 and 80, make it a little bit lighter green, and so on. And by doing this little trick here, you can get a nice little world here, okay? All right, so when you're done, you'll get something that looks like this. And in fact, if you give me just one moment, I'm gonna open up another terminal behind the scenes. You'll hear me typing. and show you what success looks like for this assignment, just so you have a reference from somewhere. Okay, so let me go ahead and bring this down here. We'll build. and you'll be able to see a solution here. Okay, as well as some of the new abstraction for this assignment. Okay, and as we're adding more to our project, it's taking a little bit longer to compile. There's ways to speed that up, but that is life. Okay, so here we are, and you can use the arrow keys to move around, shift to go up, right control, and you're welcome to remap these keys for folks. I don't think I have the mouse look here, but you can move around and see the environment here. You can see the different heights even if you scroll down here. And some of your ocean is rising, I suppose, here. It's great different waves. But anyway, this is your terrain here, okay? So you can see it's what some artist has created here. Okay, so I'll go ahead and just turn that off. Okay, so that's success. Now, we don't have to stop there. Remember, that's where we'll stop for the lab, but you can also add more detail. So other things people do to trains to start improving the quality is use multiple textures. So they'll add, because we're not just limited to one sampler, we could actually have multiple samplers. And we could do stuff like, if the height of a vertex is a particular height, it's above 20, then also blend in a second texture and give it this, grainy appearance. Maybe it's sampled from another texture, maybe you generate some noise, but that's the idea here. Okay, and this is known as multi-texturing, and that's how you sort of get these nicer trains. So here you can see it. The left side is just the color map. Maybe somebody's drawn it or procedurally generated it with an algorithm. And then the right side, you start adding some different layers to your texture to give more detail. And I would say the one on the right indeed does look much better here. You can see the fine details. Okay. Now, beyond terrains, which we've talked about, you can also use grids to simulate water, for instance. So that's where we started talking at the start of this class. We can imagine this with a blue texture on top of it. And then if I just sort of oscillate this in the, this would be in the vertex shader, the positions of the vertex or the height, perhaps I could have a uniform, for instance, that sets the height of each vertex multiplied by the sine function, right? When we're oscillating, we could use a sine or a cosine function. You get these sort of waves here. And depending on how fast you do that, it could be very wavy or whatever. But this could be another way to sort of simulate water. You could have multiple of these grids to sort of do interesting things here. Okay. So anyway, I'm going to start wrapping things up here. This is a nice sort of video supplement on terrain generation. Please check it out so you can see some of the things here. Maybe I can skip through it. I can't post too much of it here. But you can see here they're using one height map, and I think they're using another grid here to simulate the water here, as well as some different shader effects. And very quickly you get a nice scene here, okay? Especially once you start making these things semi-transparent. This is a pretty nice looking world here. And here they're just sort of walking on it. And this is another good candidate for a final project, sort of procedurally generating these trains, coloring them in, maybe doing something with water here, and so on. Okay, and here's another video nicely showing off the scaling here. So I had my little scale factor that I just divided by 5 here, but I think they show what happens when they just scale their world up. Let's see, from here, where they're sort of changing that scaling factor. So you can see how dramatic, right? Because with the height map, you've only got a range of 0 to 255. That's how many sort of discrete steps you can take. So, you might play around with it a little bit. I'm not exactly sure where this is. This looks like Honolulu or something. Oh, it's a from a video game. It's a made up place, but anyway, you get the idea with the different scaling here. Another nice example of the height map. And here you can see the wireframe. All right, so some notes on what I've seen go wrong in the lab, so you can check these out. If you've been having trouble, I'm just going to click through it, but I have a few answers here on things that you can debug. The last other thing that I want to share with folks, and let me go ahead and open up my solution again, because what you can do is there's a docs file, and let me go ahead and just open this up, because the abstraction's getting pretty big, I would say. You know, it's starting to range on, you know, for folks who have taken software engineering or object-oriented design, this project's getting pretty big. So for those who want it, or I could post it somewhere, there's a doxygen.txt file here. So if you have the tool Doxygen, and you can download it on Windows, Mac, Linux, I'm just running on the command line here, it'll actually generate some documentation for you. And you'll notice I've been trying to comment well in the codes for this. So let's just open up one of these files here really quick. Just whichever one I find here. Vertex. Let's just open up the layout, see if I get the HTML page. There we go. So anyway, you can go to the main page here. It's called, you know, whatever our course is, 4300/5310. And you can go to the classes, for instance, and see all the different classes. And, you know, sort of click around here and just see all the functions here. What's really useful is the inheritance hierarchy. So let me go to one that we're sort of familiar with here. How about object here? Object, and you're going to notice an object consists of geometry, so that's what it's composed of, vertex, buffer, layout, and textures, for instance. Okay. Terrains are derived from objects, so this is showing the sort of hierarchy here. So then you can just see, you know, the overview of the function. So if you want, this is a pretty nice documentation. Just another tip if you need. Okay. All right, so anyway, your task is to generate the triangle strip and draw the height map to set up those texture coordinates. So really 3 challenges. You'll see them as notes to do in class. There'll be other little to-do notes that are optional or just things to think about. And you can really have fun with this one. Feel free to play around with it, to try to get multiple textures, play around with the abstraction, and maybe think about how this could be a final project for you. Okay. So that's all I got for you folks today. Don't forget to do your in-class activity, and we'll pick up, as always, next week. All right, take care.